Good afternoon, everyone. My name is Emmanuel Oyedeji. I'm here to present my capstone project on Carl-Alien model, which I have done the numerical investigation of the saturation timescale on the basis of certain mobility parameters, which is taken from the model. Here we have the outline in this slide. And this outline basically is the detailed analysis of the preconditioned steepest descent, that's the PSD rather, iteration solver of a convex splitting numerical scheme to the Kahn-Inlet equation. We'll go to the next slide. Here we have the formulation variable mobility Kahn model. I'm pretty sure most people do not know what Kahn model is. I'll explain that real quick. Kahn-Inlet equation is a mathematical model of the process of a phase separation in a binary alloy. And the equations are well-known gradient flows with respect to a kind of energy, or I would say most especially free energy. Here we have the submodels, which are physical energy, chemical energy, and conserved dynamics model. So we can see the models here in equation 1, 2, and 3. So there are different methods that are used with the Kahn-Inlet model. The unique availability of the numerical scheme is derived following the standard convexity of the analysis, and the energy stability analysis could also be carefully established. On the other hand, an efficient implementation of the numerical scheme turns out to be the challenge. Due to the coupling of the nonlinear term. The surface division part and a variable dependent mobility elliptic operator. We can see here in this slide that the Euler explicit was used in telling the differences at 2 points with the time step delta t. Here we have the energy stability estimates. For the energy stability estimates, there have been extensive numerical works for the Kahn-Inlet equation. In particular, energy stability has attracted more and more attentions since it plays an essential role in the accuracy of long-term numerical simulation. The standard convex splitting scheme and Pioneer-Baer's work is very useful, and that's what was used in this approach to obtain the energy stability at a numerical level. This framework treats the convex part of the chemical potential implicitly and the concave part explicitly. We can see here in this model. Going to the other slide. So here we have the numerical results. We have the numerical results after the simulations. In the subsection, we perform a numerical accuracy for the numerical scheme, and the computational domain is chosen as what we can see here on the screen. And the exact profile for the phase variable is said to be. First thing I actually did here was to simulate numerically and demonstrate the mass conservation and energy dissipation. There are the numerical results which highlight different evolutions with constant and space dependent mobilities in a rectangular domain. The numerical experiments were reported on spinodal decomposition in the spherical and cylindrical domains too. We can see from the figure, the snapshots of the computed solution at the indicated times. We have different time intervals here. We have when t is at 100, and when t is at 200. We also have when t is at 300, 400. When we have t equal to 6, when we have t equal to 20, we can see how all of these were actually forming at different time intervals. Here we have the log plot of the temporary evolution, where we have alpha equal to 1. We can see here in this plot how the plot is being generated. In the subsection, I would say we performed a numerical accuracy check for the numerical scheme and the compositional domain was chosen, and the exact profile for the phase variable was set to be. So the first thing we did here to generate this was that we, I would say before we did this plotting, we did, the energy actually decreases, like it decreases gradually until saturation. And we can see the red line. The red line represents the energy plot, which is obtained by simulations, while the straight lines are obtained by least square approximations to the energy data. The fitted line has the form, we can see the form of the fitted lines as it goes down. Here we have the, here we have the log plot of the temporal evolution of the energy, where alpha is 0.9. We can also see here when alpha is 0.9, we can see how it moves down. As alpha increases, EH value also increases. Yeah. So this is a combination of all the sequences at different alphas with different energy. We can see as alpha increases, we can see the way all of these things are formed. Here we have a log plot of the saturation time scale in terms of alpha. We can see that as alpha increases, it gets to a point. As alpha increases, saturation time increases, but it gets to a point that when alpha increases, the saturation point decreases drastically. So here we have the summary. The summary, it tells us that, it pretty much tells us that the precondition steepest descent, as the PSD iteration solver, is considered and implemented as the first order splitting numerical scheme. You can see we had a physical model of variable mobility function, which was considered. A numerical scheme was actually applied, and this gave us an approximate physical model. And again, energy dissipation property was verified by the numerical simulation results. The saturation time increases with smaller value of alpha in general, while a few variations have been observed in the numerical results. Yeah, thank you.